Welcome. The subject of this video is how to use NPN transistor switches with microcontrollers such as the Arduino, PIC, and etc. I'm your host, Louis Laughlin. Be sure to visit my website www.bristolwatch.com for lots of stuff on electronics, theory, and other little interesting science subjects I post once in a while. First, let's take a close look at a typical microcontroller, in this case the Arduino. It's important to note that it has a negative common or negative ground and a positive 5-volt VCC. That determines a lot of how we're going to connect switches up, particularly transistor switches, to Arduino. The other important point to note is that the input-output pins have a maximum current out of 20 milliamps. Also note that you cannot hook or connect anything to an Arduino pin that exceeds 5 volts or you will damage the item. So this is our limitations, is the I/O pins have a 20 milliamp limit. We have a common ground that is negative and a VCC of 5 volts. These are TTL levels. A quick note on PN junctions, which is the integral part of transistors, diodes, and so forth. For terminology, when a junction is forward bias, it is turned on, and when it's turned off, it's known as reversed bias. That is, if you look over here at the illustration on your right, here's a diode symbol. It's actually a PN junction with the positive side being here and the arrow pointing to the negative side. It's pointing to the N-type material. That is not the direction of current flow. The negative side is called the cathode, positive side is the anode. When we apply a positive voltage to the anode and a negative voltage to the cathode, it will turn on and will be forward biased and conducting. A forward biased semiconductor junction of silicon type, its voltage on the meter, if it's made to read diodes, is 0.5 volts to 0.7 volts. Bipolar transistors come in two main types known as NPN and PNP. They operate the same but have completely opposite electrical properties. Let's look at the NPN, which is the subject of this video. The PNP will be covered in a separate video. It's a 3-pin device, has a base, emitter, and collector. The base has to be positive with respect to the emitter to forward bias the base emitter junction to turn on the device to act as a switch from the emitter to collector. We will see that shortly in the following frames. Note that transistors can come in a number of case styles, as pictured here. You need to look up the individual part number to determine what's actually in the case. It could be a transistor, could be a MOSFET, could be an SCR. The case style doesn't tell you much. On a quick note on how to connect switches, let's look at the two circuits here. On the left side, of course, on both sides we have an LED, a dropping resistor, and VCC. Note our ground is negative. Note our VCC is positive. We have to do this for the most part if we're going to connect. We have to consider that if we're connecting to an Arduino with a negative ground. In this lecture, I'm going to use negative grounds only, and it's important to note how the switches connect in the series circuit. A series circuit is where the current flows through all the devices, and it will be the same current. So the same current through the switch when pressed is the same current through the LED, through the resistor, back to VCC. Same thing over here. The order of the components, it doesn't really matter with a push button switch. It matters a great deal with a solid state switch. You can't just put them anywhere in the line. Again, note that our anode on the positive side of the LED goes to VCC. The cathode, or the negative side where the arrow is pointing to, goes to ground. Current flow, again, is negative to positive. Alright, there are two connections for PNP and NPN transistors. Excuse me, let's drop back one frame briefly and note something. Where you place the switch determines whether you are in a sink configuration or source configuration. If, for instance, you're in a sink configuration, the switch is in the ground side of the load. In the source configuration, the switch is in the high side or VCC side of the load. Source is VCC side, sink is ground side of the load. Alright, here we're looking at the two configurations for transistors. Here we have the PNP transistor on the left. The transistor acting as a switch is in the positive or VCC side of the circuit. We would say that this sources the load. In this example, it's a motor. In the NPN transistor, it is connected in the sink mode. That is, the load connects to VCC and the transistor switch is in the ground side of the load. Because of the electrical polarities of an NPN and PNP that are opposites, and because I'm using a negative ground that I have to switch it with a Arduino or PIC or whatever, these are the only way I can hook these particular devices up. I will have to connect the PNPs as a source configuration. I will have to connect the NPNs as a sink configuration. You notice the resistors here, R1 and R2. These are RB, or our base current resistors. When I press the switch, I get a base current through the emitter, through the base, back up to the VCC. That's what cuts on my current from emitter to collector through the load. Over here in the PNP side, I press a switch. Current is still coming through the base and still goes through the VCC like it did before, and it allows current through the ground, through the load, through the collector emitter. Okay, the rest of this I am only concerned with the NPN, which will be connected in the sink configuration. Alright, here we go with a transistor. It's an NPN transistor. It is connected in the sink configuration. We have a 12-volt battery. The negative of the 12-volt battery goes to the common, which is also the Arduino ground or common. We got a dropping resistor for our LED. You notice that the arrow is pointing towards the negative material, and that's going towards ground, which is negative in this case. And going back this way, it's going to the positive. Like we had before when we had a push button switch, we want to be able to turn this transistor on so it is conducting from emitter to collector, turns on our LED. Alright, let's say I need a current level for my LED of 100 milliamps. Okay, the emitter collector here is going to have to supply at least 100 milliamps to cut on that LED and make it as bright as I want it. Now we come to what is in our transistor. I chose a TIP41. That is an NPN silicon transistor. It has a maximum voltage rating of 40 volts. It has a maximum collector current of 6 amps and has an HFE of 20. What is HFE? That is your DC gain. That's also known as beta. What that means is if I have a small, let's look at the base, let's have a high coming out of our Arduino. What have we got? We got a current that comes up through the emitter. Remember, this is negative to positive. It's moving through the emitter, it's moving through the base resistor back to the Arduino. If I have, for instance, 5 milliamps coming through this part of the circuit, what it's going to do, it's going to be multiplied by 20. Okay, 5 times 20 milliamps is going to be easily 100 milliamps. That is, for an IC of 100 milliamps, if I want to know what IB is, I would divide IC by the HFE, which is 100 milliamps, divided by the HFE of 20, which equals 5 milliamps. Or you could say it the other way, it's 5 milliamps times 20 equals 100 milliamps. You can sit here and study the equations. They work pretty well out that way. Now, R1 equals the current through R1 divided by IB. Okay. That really should be the voltage. What is my voltage across R1? We got 5 volts here. Let's look at this. You notice I got 0.6 volts here. When I do these calculations, I always use 0.6. So I have 0.6 volts on the base. So that means I have 4.4 volts left on the resistor. I have to drop 4.4 volts with the resistor, and I have to supply at least 5 milliamps. Up here, I decided to use 10 milliamps. Why did I use 10 milliamps? I want to make sure that I have enough current that I can switch this transistor on fully. This puts it into a mode called saturation. When a transistor is fully turned on, it's in saturation. What that means, no matter how much more current I put into the base emitter, I can't get any more collector current. It's limited by the load. So I want it to turn completely on. I want it to be like I pushed a switch and the LED will light up. So I need an IB of at least 5 milliamps according to HFE and the 100 milliamps. I'm going to add a little extra to make sure I have enough current to fully turn that transistor on. So it's 4.4 volts divided by 10 milliamps, or 0.01 amps, and it comes out to 440 ohms. What is my total current from the emitter? The emitter, okay, remember our ground is negative, so we're going to have 100 milliamps go this way from the emitter collector. We're going to have 10 milliamps go back through the emitter base back to the Arduino. So IE, that's the current of the emitter, equals IC, the current that went this way through the diode, plus IB, the current that went this way back to Arduino, and I got a total IE of 110 milliamps. Alright, let's take a different tact here. Now I'm using a 2N3055. I need to run a motor at 10 amps. Won't work with a TIP 4040, will it? It's only limited to about, I think, 5. Nope, it's limited to 6. Can't use it. I try running 6 amps through 15 amps or 10 amps through a 5 amp transistor. Won't work. But this transistor, the 2N3055, is rated for 15 amps, has an HFE of 20. And so let's figure out, to get the 10 amps, I would have to divide the 10 amps that I need by the HFE, and I have to get a base current of 500 milliamps. That is, 10 amps will flow up through the emitter collector, back to the battery, but I need 500 milliamps to flow through the emitter, through the base, through R1, back to Arduino. This won't work. What did we say before? The Arduino can only sync or source, that is supply or switch to ground, 20 milliamps. Sorry, this will never switch on and you will damage the Arduino IO pin. What can we do? We can stick in a second transistor as shown here. We have our original 2N3055. This time I'm going to stick in a 2N2222, which is rated at 1 amp and an HFE of 100. When you connect transistors in this configuration, the HFEs will multiply. We call this a Darlington. This is not exactly, this is a type of Darlington where the collector emitter current of 1 becomes the base emitter current of a second heavier transistor. What have we got here? Connect your voltmeter to ground. You measure the base of Q1, the 2N3055, you got 0.6 volts. Drop across that emitter base junction because it's forward biased and turned on. But we have another emitter base junction up here in series with it. It also has to be turned on, so it's going to be 0.6. So 0.6 plus 0.6 gives me 1.2 volts here. I still got 5 volts in, so I have 3.8 volts I need to drop across R1. 3.8 volts. Okay, let's find out how much current we need first. Alright, let's go back up here. Look at our HFE of 20 times 100. Well, is 2,000. Now we have an HFE of 2,000. 10 amps. I still need 10 amps from my motor. Divided by the HFE of 2,000 is around 5 milliamps. Okay. What have we got here? 3.8 volts. It's dropped across R1. Divided by the 5 milliamps from the base current back to Arduino, it's 760 ohms. And so I need a 760 ohm resistor right here at 5 milliamps to give me 10 amps out. I want to make sure that I have enough current. So I'm going, the next standard size down that you should use in resistors is a 680 ohm. I would use a 680 ohm. That will assure that with both these transistors connected in the Darlington configuration, that is the emitter of one going to the base to the other, we'll get enough current to switch this on. Now, we have the second current that flows from the emitter of Q2 back up to VCC, or the positive side of the battery. I have to calculate this resistor. Well, I know that the current is going to be something like 500 milliamps or close to it. Part of the current, of course, is going to go that way. 5 milliamps will go this way, or whatever the value is. But I still got at least, let's say 500 milliamps or so coming up through here. I have to have this resistor because without it, and I switched it fully on, I would dump 12 volts straight into the base of Q1 and blow it. Can't do that. So I need this current limiting resistor, which calculates its IR2 is 500 milliamps. Well, you have to subtract 0.6 it's 1.1 volts here. You subtract that from the 12. 12 minus 1.2 volts, divide it by 500 milliamps, which is 0.5 amps. I get 21.6 ohms. I'd probably use a 20 or 18 ohms. You might get away with a 22. But that gives you an idea what's involved here. Or we could connect it like this. We could take the 2N2222 as in Q2 and connect it directly to the collector of Q1. As the voltage drops here, the voltage drop will go there. It supplies plenty of current to drive Q1 doing it like this. This is your real Darlington configuration. This is how we use a low input current to get a really heavy current. And that's going to be covered in another video. Alright, that completes a basic introduction to NPN transistor switches. Check out the other videos in this series, and thanks for listening.